Hey guys, BuildZoid here, and today we're going to be taking a look at the most ridiculous VRM on the Z590 platform, the V-Core VRM of the Z590 Godlike. It's all of this. Oops. It's all of this, and as you can probably tell from what I've highlighted, there's no iGPU power on here. So yeah, if you care about the iGPU, this motherboard doesn't support the iGPU. Personally, I don't really care that much. The only thing that I really have to say about it is, like, technically the Godlike boards are supposed to be boards that do everything, but they do everything except power the iGPU. That's one thing they very regularly don't do. So yeah, it's not a change, like it's not new for MSI to do this. It's just kind of like, yeah, if you care about the iGPU, you don't get it. Anyway, why do I consider this the most ridiculous VRM on the Z590 platform? Well, it's because of this chip right here. This chip is the Renesas RAA 229828, and this is a 20-phase voltage controller. Yeah. This is the highest phase count controller that I'm aware of. Um, it goes to 20 phases, and like, I'm assuming this was designed for like servers and, well, actually not even assuming, like, it was definitely meant for like various server platforms. And then MSI was like, yeah, we're gonna stick that on a mainstream Intel motherboard. That's exactly what we need, a 20 phase controller. Um, so yeah, I'm not sure that this is so far into the realm of like diminishing returns that I doubt there's really any benefit to having this controller, but it's cool. Um, like, yeah, that is a very neat controller. It goes up to 20 phases, also runs up to a 2 megahertz switching frequency. Not that you can take advantage of that because on this board, because the power stages don't go past 1.25 megahertz, and even at 1 megahertz, they get really like inefficient. Not that that's a huge concern with the VRM being what it is. But yeah, it's like there's really no good reason to run a VRM like this at like above 500 kilohertz. The other thing is, actually, you could probably get away with running it at like even 300 kilohertz. It wouldn't make much of a difference. One of the big reasons we have these really high phase count controllers is in fact to like minimize the switching frequency requirements, because if you have a bunch of phases interleaving, the input and output ripple frequency is actually way higher than if you had like half as many phases at the same switching frequency. Um, so yeah, but the thing is like there is diminishing returns to that, and like it used to be that like the manufacturers of the various controllers just kind of agreed that, you know, going past 8 phases is pretty pointless. And then recently we've had an explosion of high phase count controllers, and this is currently the peak of that. Because yeah, I don't know of any other chips that like the next highest phase count chip I'm aware of is the XTPE132G5 from Infineon, and that only goes up to 16 phases. And I say only when it really, like, it doesn't make a difference. It doesn't make a difference at all. Anyway, so yeah, we have this absolutely insane 20-phase Renesas voltage controller. Then for the power stages, we have the ever so popular ISL 99390s, which are 90 amp smart power stages. And these aren't really like that special. They're extreme. Actually, they're not very special at all. They're sort of the default high-end power stage of modern of like Intel motherboards for both MSI and MSI and Gigabyte, and I think Asus is even using them now, and ASRock also likes using them. So yeah, these are super common. They are expensive, like they are high end and expensive parts, but they are really common. Um, and anyway, so yeah, 90 amp smart power stages, and there's 20 of those because it's a 20 phase VRM. Now, this is not the only motherboard to feature 20 of these 90 amp smart power stages. So in terms of actual raw current handling capacity, this isn't like a step above all the other boards, because there is Gigabyte's Z590 Extreme, if I'm not mistaken, uses a also uses 20 of these, but that board has to use doublers because that board uses a ISL 69269 voltage controller, so you don't have 20 PWM outputs from the controller itself, so you need to use doublers to get up to this kind of ridiculous phase count. Um, but Anyway, so yeah, 90 amp smart power stages. These are really, really efficient. And being smart power stages, they integrate your very accurate current monitoring, temperature monitoring, and all the various safety features like overcurrent protection and short circuit protection. So yeah, this is basically as good as it gets in terms of power stages right now. Um, and so in terms of current handling capacity, what we're looking at here for 1.2 volts output voltage and a 500 kilohertz switching frequency, the combined power loss, well, the power loss, combined power loss of the inductors and the power stages, which it's not going to be super accurate because Intersil probably like the Intersil documentation doesn't necessarily is probably using slightly different inductors from what MSI ends up using on their boards, but inductors also aren't the main source of power loss in a VRM. The main source of power loss in a VRM is the actual power stages themselves, so it should be like the figures should be close enough. Anyway, let's get into it. So 200 amps output, which this is before the peak of the efficiency curve for these power stages, you're going to be looking at about 15 watts of heat output, which is great. Like if you can do, like if you can take your, for 1.2 volts, if you have a certain level of current output and you divide that by 10, and the heat loss, like the power loss of the VRM is less than that, it's a really efficient VRM. So yeah, great efficiency, but that's not even the peak of it. 300 amps is right around the peak of the efficiency curve for this VRM, because yeah, it's bloody 20 phase. You'll also notice that this is actually so much current that there's no ambient, like, okay, no, that's not entirely true. I guess with direct dye and a really extreme water cooling loop, you might be able to hit 300 amps of current draw, but under most circumstances, you're going to get stuck at around 250 amps before the chip becomes completely uncoolable. And so basically, there is no like this VRM has so many phases that even if you were like, it's not going to hit peak efficiency on any CPU that you can actually install in this socket, no matter, like, basically close to no matter how much you overclock it, right? Like you really need to go out of your way in order to even hit the peak of the efficiency curve of this VRM. Because yeah, this is really more designed for like a Threadripper than it is for anything that you would put into an LGA 1200 socket. Anyway, at 300 amps output, it would produce about 22 watts of heat. So yeah, that's where you hit peak efficiency. And so you can totally run this VRM with no heatsink, like at all. Which this is like, well, this is the thing I find sort of like, honestly, I think it would be neat if you could get these high-end boards with like no heat sinks for a significant discount, because heat sinks, especially like elaborate heat sinks like what you get on, say, the Godlike here, where it has like a heat pipe and like a real fin stack, and then there's that extruded aluminum section, and then you have, which actually I think there's a decent amount of machining on that. Then you also have the fans, and it's just like, no, this is all completely unnecessary. Get rid of the, like, that's probably, that could be like you could get rid of the entire heat sink. Just completely get rid of it. It wouldn't make a difference. Well, no, it would make a difference, but it's like it doesn't make a difference that actually matters, because if the VRM is running at acceptable temperatures, like, yeah, you can run the VRM at almost the same temperature, like at, say, 40 degrees with the heat sinks or something. But it's like the components don't care. Like, if they're running at 80 degrees or 40 degrees, doesn't matter. So yeah, anyway, 400 amps output, at which point now we're like well into LN2 overclocking territory. You're going to be looking at like 31 watts of heat output. You still don't need a heatsink. Basically, heat sinks become very necessary once you start hitting like 2 watts per component. And on this board, that happens after 500, at around 500 amps output, as now it finally produces about 42 watts of heat. Though it is worth noting that on LN2 you would be running higher output voltages, so that would actually drive up the heat output. So yeah, maybe at 1.6, like at 1.8 volts or something on LN2, you might get pretty close to requiring a VRM heatsink. And that's for sustained load. Like, the funny thing about LN2 overclocking is that the VRM doesn't really need to be that insanely efficient, because most of the benchmarks finish in less than a minute. And even if the VRM is producing like 40 watts of heat, it takes a while before it gets really freaking hot, right? Before it starts overheating. Like a lot of the motherboards that I test that like at ambient kind of suck, they might have something like 30 watts of heat dissipation, and it often takes like 40 minutes before you hit like the temperature where it's like, okay, this is not okay anymore, right? So yeah, this right here is just absolutely insane amounts of overkill. It's not the only board to go this far, but yeah, uh, this is excessive. Like already with Z490, we had a bunch of VRMs where it's like you don't need heat sinks like ever. And with Z590, the manufacturers have just taken that even further. Anyway, 600 amps output, you'd be looking at about 55 watts of heat. Now the heatsink finally becomes useful. Because this, you could deal with this with like some really basic heat sinks. So 55 watts of heat, it's like, okay, now we actually need a proper heatsink design. So yeah, current handling capacity wise, this is one of the highest power capacity, like highest current capacity VRMs on the Z590 platform. It's not the highest because, as I said, there is at least one other motherboard I can think of that has that uses the same number of power stages, and that's sort of the main factor in determining VRM current handling capacity is just like what power stages are using and how many of them. There are some benefits that you can get with like more elaborate control schemes. So something like this 20 phase might give you ever so slightly better efficiency than something using doublers or something or a board that puts the power stages in parallel. But in the grand scheme of things, doesn't really make much of a difference. So yeah, current handling capacity wise, it's ridiculous, but also not the only board to be like this. But what I'm also a really, really big fan of on this with this VRM is the actual capacitors that MSI is using. And this is a standard thing for MSI, MSI's top-of-the-line motherboards for a very long time now, is that they actually use aluminum polymer SMD capacitors for their output filters. And they've been doing this since, like, I think even the X58 days. I'm pretty sure they have a 990FX board that did this. They have a Z68, Z77, X79 boards that do this. And the reason why I point that out is SMD aluminum polymers are just better than through-hole aluminum polymers. They're also generally better than like tantalum SMD polymers. So yeah, I'm a big fan of MSI's choice of capacitors. So these are 4 volt. You can see that they're 330 microfarad, but these are 4 volt EEF SX series capacitors from Panasonic, so SP caps. And these are 9 milliohm ESR, which is kind of high. But the thing is, like, this looks kind of high, but the thing is that's that's for the voltage rating. Like, you can technically get much lower ESR SMD polymers, but you're talking about, like, 2 volt or 2.5 volt capacitors, and on a motherboard, like, then you're sort of starting to sacrifice durability for the ESR, and that's not really necessary, because the main limiting factor for output filtering capacitors is actually the ESL. And that's where SMD polymers just have a massive advantage over their through-hole counterparts, because caps with legs, just like the legs on the through-hole capacitors, just add a massive amount of inductance compared to the tabs that the SMD polymers use. So yeah, I'm a huge fan of the fact that like MSI does these all SMD aluminum polymer output filters. And also I had a bit of a look around on like Panasonic's website if there was any other capacitor that would be like a better option, and there really isn't. Like the only better options are if you go too low on the voltage rating. So yeah, it's just like this is perfect as far as I'm concerned for the output filtering on a board like this. And then other than that, on the back of the board, what I do like is we have a massive V-core power plane, right? Which you get that when you get rid of the iGPU VRM, because normally the iGPU power plane, like the iGPU connection comes into the CPU sort of through this area of the socket. But if you don't power the iGPU, you can just go like, bam. You can just put your V-core power plane something like that. And actually, there's memory over there, and there's like memory controller and system agent down here. But, you know, also, this is an 8-layer board, but you can have an absolutely massive V-core power plane, which then further reduces the resistance of the power plane and the inductance of the power plane, which gets you better power delivery. So yeah, I'm a huge fan of this VRM. Like a huge fan of this VRM. It's a real shame that the only motherboard that MSI offers it on is a $1,000 motherboard. And honestly, I'm not even like I don't even necessarily care that much about the controller. It's just like I wish they would take this output filter and put it on some cheaper boards. It is an expensive output filter, to be fair. SMD polymers are not cheap, especially when you're going for like 4-volt rated ones. But yeah, like I don't want all the other parts this board comes with that drive up the cost. It's just like these caps, thank you very much, and then the power stages. And we also don't need like this many of them. So anyway, yeah, so this and so the benefits of having these like low ESR, low ESL capacitors like these SMD aluminum polymers is that it should get you much better transient response, along with the larger power plane that should also lead to better transient response from the VRM. So this is a board that I'm very interested. Like basically, this is one of the few boards where it's like I think this might be better than all of the Z490 motherboards I tested. Though this VRM is also not that different from the VRM that MSI had on the Z490 Godlike already, and I unfortunately never got a chance to test that board. So yeah, I'm kind of well. So you know, we'll basically be comparing this really ridiculous VRM from MSI to some of the like Gigabyte Z590 boards, and then a lot of the different and then a lot of the Z490s that I tested. I've like the thing is on Z490 it already looked like we were hitting the limit of what the socket is capable of doing in terms of transient response. So I'm really wondering if like this combination of like direct 20 phase VRM and these real like this as far as I'm concerned are the best capacitors I've seen on a motherboard for the output filter. Just straight up, I can't think of any motherboard. Like Gigabyte gets kind of close with their tantalum polymers, but tantalum polymers are still slower than like aluminum polymers the vast majority of the time. Um, and so yeah, this is like if there's any board that's going to improve on the transient response of like the Z490s that I tested, it's going to be this or maybe the Tachyon. Maybe they'll end up tied for first place. That wouldn't really surprise me because my oscilloscope isn't really like, my oscilloscope only measures down to 10 millivolts. So yeah, it's not going to pick up on very fine, like very small differences in transient response. Also, I wouldn't really like consider a 5 millivolt voltage regulation difference is kind of like, it doesn't matter. Um, so anyway, um, yeah, this VRM right here is just, as far as I'm concerned, this is probably as good as it gets. The one thing that is arguably kind of lacking compared to some of the other high-end motherboards is the input filter. MSI has, like, it's really basic, right? You've just got your two bulk capacitors over here and your two bulk capacitors over there, and that's it. Like, and I don't really think there's anything particularly wrong with that, especially considering like this is a 20-phase VRM. The switching noise from this VRM should be just naturally extremely low because it's got such a high phase count. Um, but yeah, it's an interesting difference compared to say like well actually for a long time this would be like on par with what Gigabyte was doing for their input filtering, but compared to say Asus and ASRock, Asus would, for a motherboard in this category, Asus would normally use like 8 capacitors instead of just 4, and then ASRock's input filtering is like really elaborate as far as I'm concerned. They basically have the most elaborate input filters I've seen, usually using like a really weird mix of very large multi-layer ceramics and tantalums and through-hole capacitors. Like it kind of looks like they just shove whatever capacitors like it's really excessive in my opinion what ASRock does, but unfortunately I've not had a chance to test one of the boards with that input filtering. So I'm not like, because the thing is ultimately I don't really necessarily care that much about how like what the switching noise on the input of the VRM looks like. What I care about is what the transient response on the output is like. And I'm kind of wondering is like, do you actually get a usable benefit from having a really elaborate input filter? Like what say ASRock has. But now even like high-end gigabyte boards will have, say, well, the Tachyon, for example, just uses, I think, like 20 tantalum polymers for the input filter, which is also like really like that's a really nice input filter right there. So yeah, this board's VRM is sort of, well, I like it. I really like it on paper. Right, really high current handling capacity, should have amazing transient response because of the combination of massive power plane, no doublers, really nice SMD aluminum polymer capacitors. So yeah, and then the only thing I'm kind of wondering about is like, well, the input filter looks kind of weak, but also in my experience, input filtering just like when it comes to the output power regulation, it's like the input filter doesn't really matter that much, which would explain why, MSI is just going with sort of 4 capacitors for it. So yeah, this right here is probably one of the best VRMs on Z590. If not the best VRM on Z590. Like, you'd need to test that, but I would not be surprised if it was the best. Also, it might just be, like, it could also end up just being tied with a couple other boards, or many other boards. Like, it really depends if the Z490 boards actually maxed out the CPU socket, then yeah, then even something like this is just not going to lead to any benefits, which would be kind of a shame, but hey, it is a really nice VRM. Anyway, down here we have the system agent rail, and that's just a 50 amp power stage for that. And what else do we have? Oh, well, I guess we could talk a little bit about the memory. So this board uses the board uses an 8-layer PCB, which I'm not sure. Yeah, no, you've got the layer count indicator down there. So this is and actually, like MSI, I think straight up says that this is an 8-layer PCB, which incidentally, they also have an 8-layer PCB on the Ace board, which is kind of, and the reason I bring that up is like basically that means the Godlike and the Ace should have basically the same memory overclocking capabilities because they can use the same memory topology for both of them because the layer count is the same. But anyway, so you've got an 8-layer PCB, and then in terms of the actual memory topology, we're looking at a daisy chain. So this board is going to favor running 2 memory sticks instead of running 4 memory sticks. But MSI's, like, in my experience, MSI's boards are really good, like really flexible in terms of their memory support. So even with 4 sticks, you should have pretty good results, if not great results. So that's just kind of like, yeah. Unfortunately, the board I have is like an early engineering sample, and I've been told that they basically didn't finish the memory optimizations on the board that I have. So I can test the VRM. I can't, unfortunately, do anything when it comes to the memory side of things with the board that I have. And the other thing that's interesting about MSI's daisy chain topology on Intel boards is that they use these really weird looking traces, and these are called tabbed traces. And the idea, and what these are supposed to do is they're supposed to reduce the crosstalk. Am I writing that correctly? Is there 2 B's in that? I'm not entirely sure. Oh yeah, there is. So yeah, you have these tabbed traces. And they basically reduce the interference between the different memory, between the memory signals. So, yeah. And I'm not sure how this, again, I unfortunately can't test this board for memory overclocking because I have a engineering sample which is apparently very unfinished. But the VRM part of it is done, so we can test that. Yeah, on Z490, my experience with like the 6-layer, and that was on a 6-layer board, daisy chain with tab traces, like it was good. It was really good. It ran like a lot of different memory configurations, ran on it just fine. So with, 2 more layers and a new iteration of the design, I would assume it's just gotten better since then. So, yeah. Anyway, that's basically everything I want to cover in this video because I already did a video doing a feature over... Actually, no. The one thing I forgot to mention, because I did a video with this board in the past where we did like a feature overview. The one thing I forgot to mention in that video was that this board does have dual BIOS, which is, of course, a feature I'm a big fan of because if you want to test like different BIOS versions... like if there's a new BIOS version and you want to test if it's better, well, you can just put it on the secondary BIOS chip and then switch between them to do like back and forth, like very quick back and forth testing between the two BIOS versions. Anyway, yeah, that's it for this video. So, it's a real shame that this VRM's on $1,000 board. Like, yeah, and also well, like, so yeah, like this is the most ridiculous VRM on the Z590 platform. Unfortunately, motherboard vendors have also decided that Z590 motherboards get to have absolutely insane price tags. So it's kind of like like the only way buying this board makes any sense is if you already have a 5950X. And you might be like, wait, why should you have a 5950X? This is a Z590 board. Well, you see, the 11900K is a bad CPU. So first, get a 5950X. Get yourself like a pair of RTX 3090s. And then once you have a pair of RTX 3090s, you've already made at least one really bad purchasing decision. So now you can go and buy a Z590 Godlike and an 11900K because it won't look disproportionate to what you've already done anymore, right? That's like the only way I could make sense of getting this board is just like if you already have absolutely everything else, and you're buying it more as like a collector's item than an actual like motherboard that makes sense, because it doesn't. Yeah, like this is a really cool VRM. It's just it's not. I don't think it's a. I don't consider it $1,000 of cool. So yeah, that's the Z590 Godlike. I wish we could get like a light version where it's literally just the VRM and everything else missing. Also with 2 DIMM slots. Because of course, you know, like you can have a strong a strong daisy chain isn't too bad in a 2 DIMM configuration, but it's still not as good as just having 2 DIMM slots instead. So yeah, there. That's actually it for the video. So thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can, you know, buy the usual YouTuber merch like shirts, stickers, posters, that kind of thing. And yeah, both the Patreon and Teespring help out immensely with running the channel, so it would be much appreciated if you'd check them out. And that's it for the video, so thanks for watching, and goodbye.